For each of the following situations, represent the object with a particle. Then sketch all the forces acting upon the object, letting the length of each vector represent the magnitude of the force. Which of the objects are in translational equilibrium? Alright, so for this first one, it's the simplest case, a box lying motionless on a surface. Over here on the side, I'll represent the object as a particle. Now, Earth always pulls down on objects of mass, so there should be a force of gravity pulling the box downward. I'll label it FG. I won't use agent-object notation on here just to save space. Are there any other forces acting on the box? Well, if that was the only force acting on the box, then the box would accelerate downward toward Earth. But we know that it's motionless, so the forces on it have to be balanced. The only other force could come from the table or ground that it's resting upon, and that'll be equal and opposite to the force of gravity. Now the forces are balanced. This is an example of translational equilibrium. And one of the things that translational equilibrium implies is that there is no acceleration. This is the type of diagram that you want to draw for each situation. And you should try them for yourself before viewing my answers. So I'll give you a minute to try them, and then I'll give the rest of my answers. This box is sliding at constant speed without friction. Let's represent it as a dot. Now, when the object is moving across ground, it still feels a force of gravity. And it's still in contact with the ground, so it feels a normal force too. So some people will tend to put a forward arrow for this diagram. And they do that because they see that the box is moving to the right. Now, in the old days, Aristotle had the idea that a force was proportional to the velocity. And what that meant was that if an object is moving, then there has to be a force causing it to move. Okay? And sometimes this force was thought of as some kind of fluid that flows from a person who pushes it to the box, giving it a certain energy which dissipates throughout time. However, Sir Isaac Newton had a different idea. What Newton said was that if we had a force in the forward direction like this and it was unbalanced, then that would cause the box to accelerate. So this would be the diagram for a box that is accelerating, moving faster and faster as time goes on. But they actually said the box was moving with constant speed. And there's no friction. So if there was friction, then we could balance off that forward force. But according to the givens, there is no friction. So what do you think Newton said about the forward force? Well, Newton disagreed with Aristotle. He said that in order for an object to move at constant speed, the forces actually have to be balanced. And the only way for these forces to be balanced is if that forward force doesn't exist. Anytime you put a force vector in, you want to think about who or what is causing the force. So if that force was there, you'd have to think about why is it there? Somebody pushed the box to get it going, but nobody's pushing the box now. It's just sliding on its own. So, whereas the force was there when it first got pushed, the force is not there anymore. So this is actually the correct diagram for a box sliding across ground with no friction. And we see that it is in translational equilibrium. Here's a box that's slowing due to kinetic friction. The box still feels force of gravity. It still feels a normal force. Now, friction acts in the opposite direction of motion. I believe that these markings are supposed to show that the box is slowing down, like these are where the box was located previously. It was moving quite fast, then it slowed down. So there has to be a force of friction that's opposite the direction of motion. That could look like this. Now, this diagram is not in translational equilibrium because there's an unbalanced force. And the box is actually decelerating, slowing down. Now on a ramp, things are a little different. Gravity still pulls directly downward. However, sometimes people want to put the normal force straight up. But that actually isn't right according to the mathematical definition of normal. The mathematical definition of normal is perpendicular to a surface. So what actually happens is, yes, the gravitational force pulls down, but the normal force will act at an angle, making a 90-degree angle with the surface of the ramp. So we'll have this. And technically, this is considered an unbalanced force. The arrows aren't 180 degrees opposite from each other, so they don't actually cancel each other out. And as we can see, the box is accelerating down the ramp. Here, static friction prevents sliding. Gravity pulls down, the normal force goes at an angle, and now there's one more force involved. This frictional force has to be parallel to the surface of the ramp. Static friction means it's friction that's there even though the box isn't moving. So we'll have this, and now a force going up the ramp. That's the force of friction. Is it possible that these three forces will balance each other out? It actually is possible. As we can see, the box is at rest. So the forces must be balanced, and it's in translational equilibrium. An object suspended from the ceiling will feel a pull from gravity, and it doesn't fall, so there's going to be a tension force that balances with the gravitational force. Tension forces can be redirected in many different ways depending on which way the cable is pulling. So here we can have this situation, FT, FT, FG. Oh, and these are both in translational equilibrium. Here's the answer for the next one. This is in translational equilibrium. All right, for this one, we're going to have a gravitational force and a tension force. And the way that these forces are balanced is there will also be a normal force. And the last one here, two normal forces. One supplied from the surface on the left, and one supplied from the surface underneath it. Okay. What about an object that's attached to a pulley, where the object is being pulled upward at a constant speed? Now, I think we can all agree that gravity will act on this block. And the question is, how large must the tension force be, which is pulling that box up? Now, sometimes people want to put a larger arrow for the tension force than they do for the gravitational force. It's just instinct, you know? Because when an object moves in a certain direction, you think, well, there must be a reason for that. It must be a push or a pull that's causing it. But there are keywords here that make us know that that's not the case. The keywords are constant speed. If this were the free body diagram for the thing being pulled up, it wouldn't be going at constant speed. It would be accelerating in the upward direction. But they didn't say it was accelerating. They said it was just moving at constant speed. So according to Newton's first law, that's not the case. Surprisingly, the tension force and the gravitational force have to be equal at that time. And our box is in what is called translational equilibrium. All right, how about the forces for this? There will be a force of gravity, and there will be a force which is directed at an unusual angle here. I'm just going to move the arrow though so that its tail is on the dot. That's just kind of conventional. Then when we do the normal force, what will happen is sometimes people put the normal force to be equal the gravitational force. But actually what happens here is when you push at a downward angle like that, you're making the table respond. The table is going to have to supply a larger force to stop your force. So the normal force actually increases substantially when this happens. And that's the diagram. Now, they didn't say whether there was friction or not. So if there's friction, then there could be translational equilibrium. If there's no friction, then there wouldn't be. So it sort of depends for that one. According to the diagram I've drawn, the box would be accelerating because there'd be an unbalanced force in the x direction. All right, an object falling with no air resistance. When we're in free fall, we remove the normal force that used to be there. See, when it was resting on the surface, it was in contact, and that contact could supply a normal force. Here, there's no contact, so we only have the gravitational force. And this would not be in translational equilibrium. It's an unbalanced force, and that's why our object accelerates toward ground. If we have constant terminal velocity when we're falling, like a skydiver, for example, then the air can supply that upward force which resists motion. I'll call it F air or F drag. This is translational equilibrium. When we're rising toward a parabolic trajectory, as long as there's no air resistance, we only feel one force, the downward pull of Earth. And when we're at the peak of the trajectory, it's the same. I'm neglecting air resistance though, because air could supply forces to that ball opposite the direction of motion. Both of these cases include unbalanced forces. Finally, what about a book that's resting on Earth's surface? First, I'll let the book be the system. The book is pulled down by Earth. Earth on book. Simultaneously, though, the Earth stops the book from falling into itself with a normal force.